Bismillahirrahmanirrahim. Now, after doing a little bit revision of set theory, we will start our main topic of probability. We will start with the very basics of probability, and although we assume that most of the students of engineering already are familiar with these definitions and terms, but in case if somebody is not familiar with these terms or has forgotten, we will go through these terms once, so it will help us to understand the advanced topics. So first of all, what is an outcome in probability? An outcome of an experiment is any possible observation of that experiment. Means if you are performing an experiment, for example you are tossing a coin, and whatever the result is, whether you get head or tail, that will be the outcome of the experiment. Implicit in the definition of an outcome is the notation that each outcome is distinguishable from every other outcome. It means that the outcomes are independent of each other and they are distinguishable. Like for example, you have tossed head, or you have tossed a coin and you get head, and next time you toss a coin, then the probability of getting head or tail is independent of what you got previously. As a result, we define the universal set of all possible outcomes. The universal set of all possible outcomes is called sample space. The sample space of an experiment is the finest grained, mutually exclusive, collectively exhaustive set of all possible outcomes. Now we will go through all these terms one by one. What do we mean by finest grain? Finest grain means that all possible distinguishable outcomes are identified separately. Finest grain means that the outcomes are distinguishable and they are identified separately. And by mutually exclusive, we mean that if one outcome occurs, then no other outcome also occurs. Means just like in null sets, we say that two sets are mutually exclusive, when it means there is nothing common in between these two sets. Similarly here, when we are talking about outcomes, then no other outcomes also occurs mutually at the same time based on that experiment. And collectively exhaustive means that every outcome of the experiment must be in the sample space. So all the possible outcomes are there in the sample space. So if you have got any such set, it is called sample space. A sample space is a set in which the outcomes are finest grained, mutually exclusive, and collectively exhaustive. Now we'll see the example of sample space. Sample space for a coin flipped one time. Observe the sequence of heads and tails. So if you are flipping a coin just once, so what are the possibilities? Of course, either you will get head or you will get tail. So these head and tail are finest grain, mutually exclusive, and collectively exhaustive, because there are only two possibilities, head and tail. But if you flip the coin 3 times, in that case the sample space will be different, and in that case the sample space will be all the possible combinations of head and tails. And here you can see that this outcome that you get head is independent of this outcome, and this outcome is independent of the other one. So these outcomes are again exhaustive, mutually exclusive, and finest grain. Exhaustive means that there are only these 8 possibilities: 1, 2, 3, 4, 5, 6, 7, and 8. These are the only 8 possibilities. Either you get all the heads, or you get all the tails, or you get head tail, or head tail head, something like that. So these are the only possibilities. Sample space for a coin flipped 3 times. Observe the number of heads. So if you are just talking about number of heads, so either you get no head in case of you are getting all the 3 tails, so in that case your number of heads will be 0, or you get all the heads, in that case your number of heads will be 3. Here you have got other outcomes where you have got two heads, like this one, this one, this one. Here you have got two heads, and then you have got possibility of getting just one head. For example, like this: head, tail, tail, and tail, head, tail. Here you are getting only one head. Event. An event is a set of outcomes of an experiment. Event is a set of outcomes. So whenever we get a set of outcomes, it is called an event. So if we compare this with the set algebra and probability, the terms event and set are the same. When we are saying event, actually we are referring to a set. When we say sample space, actually we are referring to a universal set in set theory. And when we say outcome, actually we are referring to elements, because here you can see that all these are written in set form. So this head, 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 and head, tail, head, they are elements. And if this S is a universal sample space, in that case it is a universal set, where it means that it has got all the possible elements. And of course that these are written in form of set, as we are written, it is written over here. And set is nothing but event in probability, in terms of probability. So this table relates the terminologies of probability to set theory. Defining the sample space and its outcomes are key elements of the solution of any probability problem. We'll see the importance of this one when we'll talk about some real practical applications of the probability, or when we'll be trying to develop models for experiments. A probability problem arises from some practical situation that can be modeled as an experiment. This is an important statement. A probability problem arises from some practical situation that can be modeled as an experiment. To work on the problem, it is necessary to define the experiment carefully and then drive the sample space. Getting this right is a big step towards solving the problem. So whenever you have to solve a problem, first of all you need to define the experiment carefully, and then you have to drive the sample. For example, over here you can see, if you have not defined the sample space correctly, for example you define sample space for 3 times like this, just head and tail, then of course your sample space is wrong. And when your sample space is wrong, then you cannot model it properly. So to have a proper model, first of all you need to have the correct sample space, and to have the correct sample space you need to understand the experiment by itself correctly. So what are the example of events? Suppose we roll a 6-sided die and observe the number of dots on the side facing upwards. We can label these outcomes I is equal to 1 to 6, where I denotes the outcome, and and the outcomes that I dots appear on the up face. The sample space is S is equal to 1, 2, 3, 4, 5, and 6. So this is important, because we know that if you have got one die, then the possible outcomes are either you will get 1 or 2 or 3 or 4 or 5 or 6. You cannot have any other number. So each subset of S is an event. This is our sample space or universal set, and whatever set we have which is a subset of this S is an event. So for example, this is an event E1, where we say that roll 4 or higher. So it means that numbers which are 4 and greater than 4, so that is the set will be 4, 5, and 6. There is another event E2, the roll of even numbers. So what are the even numbers in this set? 2, 4, and 6. So the event is 2, 4, 6. It means what you are observing, you are just observing when you are getting after performing the experiment or throwing the dice, whether you are getting 2, 4 and 6. You are not interested in other numbers. But if you get 1, 3 and 5, you are not interested. Just you want to know how many times you get 2 and or 4 or 6. It means only these even numbers. And this E3 is that the roll is the square of an integer. So for the possible numbers are only 1 to 6, and square of an integer number 1, square of 1 is 1, and square of 2 is 4. So any squaring 3 will be 9, which is out of this set, and all the other numbers will be higher. So in that case, the possible event is 1, 4, or the possible set is only 1, 4. Wait for someone to make a phone call and observe the duration of the call in minutes. An outcome x is a non-negative real number. So the sample space is s is equal to x given that x is greater than equal to 0. So this is the sample space, because we don't know how long the call will be. Duration of the call we don't know. It is in minutes, but it can be it is not limited by any number. So any value greater than or equal to 0 will be part of this sample space. The event, the phone call, lasts longer than 5 minutes. Now here we have we are making a subset of it. What is it? What is the subset? The phone calls last longer than 5 minutes. So what is the event in that case? E is equal to x given that x is greater than 5. Means the calls which are less than 5 minutes, we are not interested in those calls. We are only interested in the calls which are greater than 5 minutes or longer than 5 minutes. Mutually exclusive events. Two events are said to be mutually exclusive if they can't both happen at the same time. So for example, let's consider two events A and B for flipping a coin. A is equal to head and B is equal to tail is up. So if we get head, we call it A, and if we get tail, we call it B. Clearly the coin flipping must result either in head or tail. It can be both. So here the events A and B are mutually exclusive, because if head, where you will get head on upside, then you cannot have tail, and if you get the tail, then you cannot have head. So these head and tail are mutually exclusive. Now what are the events which are not mutually exclusive? So when throwing a fair die, the event getting a or an a 1, so the event getting a 1 and the event getting a 4 are mutually exclusive, because they can't occur at the same time. So if you'll get 1, you cannot get 4. If you'll get 4, you will not get 1. But the event getting a 3 and event getting an odd number are not mutually exclusive, since it can happen at the same time. So for example, if you get 3, then both the events have occurred. You have got an odd number and you have got 3 as well. Other than 3, if you get any number, odd number other than 3, then of course it will not be the same. But the probability of getting 3 and getting an odd number is there. So these two events are not mutually exclusive. Whenever you will get 3, you will get this event as well. So these two events are not mutually exclusive. But getting a 1 and getting a 4, they are mutually exclusive, because if you'll get 1, you cannot get 4, and vice versa. So there is another example of mutually exclusive and not mutually exclusive. Here you have got aces and kings. So aces and kings are mutually exclusive, because it's not possible they are both. I mean, if you get aces, then you cannot have kings, and if you get kings, then you cannot have aces. But getting hearts and kings is not mutually exclusive, because you can have a king of heart. So this event, if you are looking for hearts any heart, doesn't matter whether it is ace or 2 or 3, and you are looking for kings as well, then it is possible that these both events occur together in case if you get king of heart. So these two events are not mutually exclusive.